Yeah, so what is the unit of moment? So if you look at the liquid, if you look at the equation, so this is force times distance, so that is Newton times meters. That's why the SI unit is Newton meters per moment. Okay. Now, okay. I think it's clear for you that because a force is acting downwards at this edge, the bar will actually move like this. From its initial position. Okay.
Yeah.
That's why this is what moment is all about. So there's a turning effect due to this force. Okay. Now, what are the conditions for an object to be at equilibrium? That is to be where exactly it is. So what are the conditions for it to be stationary? That is having no such turning effect. Two conditions: the sum of moments about any point is 0. Second condition is the vector sum of forces on object should also be 0. So the sum of the forces and the sum of the moments both needs to be 0 to actually reach equilibrium. That is having no no change in state of rest or motion. Okay.
What is the vector sum?
Vector sum.
The total sum.
Yeah, so vector sum, why did I mention vector? Because obviously force and moments, all of these are vector quantities. So for example,
Yeah.
let's say a force is acting downwards, which is, okay, let me give you a good example. Just think that this is a bar and a force is acting downwards. This is F1 equals to 20 Newton. Okay. And then another force is acting upwards. So this is F2, which is equal to, let's say, 40 Newton. Okay. Now, what will be the vector sum of the two forces? Obviously, if we take upwards as positive, you can actually write 40 minus 20. So that is 20 Newton upwards. Okay. So that means the bar will actually move upwards. Okay. Because the resultant force is going upwards, the resultant force of 20 Newton.
Yeah.
It won't be stationary, it won't be in equilibrium. Now, what if this F2 is 20 Newton? So this is 20 Newton going upwards. So again, if we take upwards as positive, then 20 minus 20, that is 0. 0 Newton acting on this bar.
But it's in equilibrium, right?
Yeah, but then you also need to check the moments, the sum of the moments acting on this bar to actually, conclude that whether this bar is in equilibrium or not. So it's not just the forces, the summation of the forces, but also the summation of the moments that you have to check.
So it can't be either one of them unless both of them are 0. Then it can be said that it's in equilibrium.
Yeah, exactly. Both of them needs to
Alright.
be 0.
Yeah.
All right. For example, this one will actually, the bar that I drew over here, this one is actually not in equilibrium. Why? Because let's choose this point as the pivoting point. You'll see that this force creates a moment that makes it move clockwise. Even this force creates a moment that makes it move clockwise. So then sum of moments is not 0. It's actually creating a moment. So it's not in equilibrium. It's supposed to rotate like that. Okay. Yep. Is that clear? Are there any questions?
Yeah, it's clear.
Okay. Now let's talk about the principle of moments. Principle of moments states that for an object in equilibrium, the sum of clockwise moments about any point is equal to the sum of anticlockwise moments about the same point. So yeah, like I mentioned before, for an object to be in equilibrium, the sum of the clockwise moments should be equal to the sum of anti-clockwise moments so that they cancel each other out, and then eventually there are no moments at all. Okay.
Yeah.
In the previous example, the small example that I gave you, like I said, the force 1 was creating a clockwise moment, and even force 2 was creating a clockwise moment. And if you check their magnitude, you'll actually see that the magnitude is the same. I'm going to go back to this one. Yeah. So let's say this distance, let's say this is the middle point of the bar, and both of these forces are acting at the very edge. Okay. Yeah, so let's say this distance is 10 meters, even this distance is 10 meters. Then the moment created by F1 is 200 Newton meter clockwise, and even the moment created by F2 is 200 Newton meters clockwise. So that means the sum of the two moments is actually 400 Newton meter clockwise. It's not 0 at all. Okay. So yeah, resultant moment should be equal to 0 Newton meter for an object to be in equilibrium. Yeah, I hope that's clear.
Yeah.
Now we can talk about center of gravity, or CG. What is it? So the CG of an object is the point where the whole weight appears to act on. Now, this point will not change regardless of how the object is oriented. So however it is placed, the center of gravity is always the same for a particular object. The CG, now the center of gravity can sometimes lie outside of the object, interestingly. Sometimes, especially for hollow objects. Yeah, I'm going to give you an example. Let's say we have this metal ring. Okay. Yeah, mine doesn't look exactly circular, but yeah. Then the middle point right there, that is the CG of the metal ring.
Apu, the middle part, it's hollow, right? And yet
Yeah.
the center of gravity is in the middle.
Yes.
I'm done.
Okay. Do you also have stability? Let me check. Yeah, stability. Stability of simple objects. Okay. Let's start stability. It is the ability of an object to retain its original position after being displaced slightly. That is the stability. Yeah, you need to know, there are certain characteristics of a stable object, unstable and neutral. Okay, let's make a table. Let's say these are the characteristics of a stable object. This is for unstable, and this one for neutral. Yeah, for a stable object, the base area is usually large, and for unstable, it's quite small. For neutral, there should be one line of contact or points of contact with the surface. I'll explain this in a minute. Well, I'll show you in a minute. What about the height of the center of gravity? Where should it be for stable objects? The center of gravity of stable objects are usually, placed quite low. For unstable, it's at a high position. And for neutral, it's in the middle.
Also, the height of the center of gravity means the height of the object low, or the center of gravity that's low.
The center of gravity. So for example, let's say a rectangular object. It is more stable. So if it is placed like this, because then the center of gravity is right there. So you can see that, yeah, this is the height. But if you place it like this on its width, yeah, then the height is the height of the center of gravity is quite higher, and this is less stable. This is more stable. And as you can see, the base area, it's quite large. This base area is very small. Okay.
Yeah.
Next is slight displacement from equilibrium position. Slight displacement from equilibrium position. So for stable object, it will return to its original position. Unstable, for unstable object, it will topple over. If to toka dile pora jabe ar eta a stable object will return to its original position because it has a higher stability, and neutral one will stay in a new position. It will move, but it will stay in a new position. Can I remove this rectangle?
Yeah, sure.
Hello.
Well,
Yeah, okay. So are you following me? So let's give some examples of stable objects. So for example, sorry? Hello?
I couldn't hear you before, but I think I can hear you properly now.
Okay, now it's clear.
It's clear now.
So this is a classic example. Let me give you more examples. So this is a cylinder. This is another cylinder with smaller base area. And this is another cylinder. Okay. Now, how can you improve the stability of an object? Number one is you can lower its center of gravity. How? By adding weights to its lower part. Or you can increase the base area. Okay.
So the cylinder in the large, the cylinder, its surface area is different from that in the neutral, right? They're both lying down, but it's different.
Which one? The cylinder in the neutral.
Yeah, the cylinder, or are there different cylinders in the stable and the neutral one?
Yeah, well, the stable cylinder that I drew that has a larger base area. But yeah, if you sort of put it in a, if you make it lie down on its side, then it is definitely the neutral state. And if a cylinder has a smaller, cross section, so a smaller base area, and if you make it stand like that, then it is definitely unstable. Okay.
Yeah.
At least if you make it, lie down like that, it will be in a neutral position. Okay, great. I think we are done with this chapter. Um,
I have a quick.
Sorry, hello?
In this,
Hello?
as how to determine the position of the center of mass of plane lamina. Mass to show us.
Mo, тоже структурировано интернет. I couldn't hear you. Can you repeat again? मैं वेर है इस इंटर चाल